Okay, everyone can hear me and see my slides, yeah?
Yes, Doctor.
All right. All right, so this is lecture number 5. So in the previous classes, we've looked at the basic principles of stratigraphy, how stratigraphy is controlled by the interaction between relative sea level and sediment supply. Okay, and you get different kinds of patterns to the stratigraphy based on differences in the interaction between the two, different rates. Right? We also looked at the concept of sequence stratigraphy, where you get when you have these relative sea level cycles, you get also cycles in the stratigraphy, and these cycles are called sequences. And the sequences always begin and end with an unconformity, and it's called relative conformities. Okay, so the boundaries of your sequences are sequence boundaries, and depending on where you are on the sea level curve, which phase, right? Are you is sea level going down very fast? Is it rising very fast? Is it in between? You get different expressions to the stratigraphy, different patterns, and these different patterns to the stratigraphy are packages that we call systems tracts. Okay, and we've looked a little bit at the different systems tracts. How if you have perisequences, how will they be arranged, right, during different during different systems tracts. So let's go dive a little deeper lah in looking at the details in each systems tract. That's what we're going to do today. Okay. Back to this. So we're going to today we're going to look at the vertical patterns of systems tracts. Yeah. So this is a cartoon model of sequences. Yeah. So you have a high stand systems tract here, HST, green, and it's overlain by an LST. So you have a sequence boundary here, so a sequence boundary here, followed by a TST and then another HST. And then you have another sequence boundary here, and that's going to be a single sequence, right? And depending on the systems tract that is preserved, if you have parasequences, you get different kinds of patterns. Right? For example, if it is LST, your parasequences will showing a initial progradation, the prograde dulu, it goes towards the front, but then it starts to aggregate because sea level is starting to rise faster. During the TST, all your parasequences form a set which is retrograding. Your shoreline is moving backwards and backwards and backwards because it is transgressive. Okay? So we put the abbreviation there, R. During the high stand, it aggregates, then it progrades, because relative sea level is slowing down and starting to fall. When you get a fall, you get another unconformity at the top, right? So you get aggregate to prograde, degrade kind of pattern. And the cycle continues with another sequence at the top. But that is a very simple story. Itu cerita yang mudah je lah. One problem with this story is that not everywhere you get parasequences. You don't get parasequences everywhere. Parasequences tidak hadir di semua tempat. Parasequences are easy to identify on the shelf, in this part here on the shelf, along the coast, where you have deltas and shore faces. So you get these sedimentary packages, the coastal packages. And when sea level rises, you get a flood. And aras laut naik, banjir lah. In other places, if you are in the deep marine environment, you don't get parasequences. The problem is everything's already deep water, and even if you change even if there is a change in relative sea level, goes up and down, water depth is still very deep. It's probably several kilometers deep, so it's not much in difference, right? And during very high sea levels, nothing. Most of the sediment is trapped on the shoreline anyway. Not much reaches the deep marine environment. Okay? The same problem also with fluvial environments on the continent. Di atas kawasan darat, where you have rivers. So that's another place where you don't have any parasequences, because in order to identify parasequences, you need to be able to pick flooding surfaces, right? But if you don't have any marine waters here, how can you pick flooding surfaces? It's difficult. Okay. And also, different kinds of tectonic activity might be happening in the fluvial area here compared to the shelfal area here. Right. There's more probably maybe some places a higher degree of subsidence and so on. Okay. So, different parts of your sequence will have different kinds of patterns to the sequence stratigraphy. Sedimentary basins are large and mostly buried. It's under lots and lots of more sediment, several kilometers underground most of the time. Stratal terminations, large-scale geometries are observed clearer using geophysical methods such as seismic. Okay. When dealing with small exposures or one-dimensional data, things like well logs and cores, vertical, stratigraphic, and fascist patterns can be used to interpret sequence stratigraphy. So what does this all mean? So in this picture, you can see all the sequences. Very nice, and I can see the HST and it's prograding. The TST is retrograding, and this is a downlap surface, so that must be the maximum flooding surface. Now the problem is, this is a picture of the whole basin, right? You can see individual layers being. You can see the lobes and basin floor fans and so on. And basins are very big things, right? You can make this in small experiments also, like in things like flume tanks and something like 100 meters wide, tens of meters wide, and so on. But yeah, in nature, a lot of basins are very big, right? Kilometers to hundreds of kilometers wide sometimes. Yeah. So you need tools that can see the larger picture in order to see all these stratal patterns. Things like seismic. Yeah. Using seismic, you can see these kinds of patterns. But what about if you are not working with seismic, right? Maybe you are just working on an outcrop. Like you've worked with outcrop before, kan? Maybe in Perlis ke semua tu. You've gone to the field and the outcrop in Malaysia, it's not going to be very big. 100 meters wide and 50 meters thick. Right. Now, so in that very small exposure, how do you identify patterns in the stratigraphy and interpret them in terms of relative sea level change, right? If you cannot see the whole picture? Well, you can also see patterns at the small vertical scale. Maybe you only have a limited sample like this. There's going to be a vertical pattern to your stratigraphy. Okay? And we can use those vertical patterns to identify the interaction between sediment supply and relative sea level change. Okay, so you get different kinds of patterns during TST, HST, LST, and so on. Okay, so this can work with outcrop. So you draw a sedimentary log and you find the patterns. You cari corak the sedimentary log. Or you can use it for other kinds of samples, things like well logs. Right. So a well log is just what? It's just some kind of geophysical signature you are detecting, and then depth. It's a log basically, and some logs are very good at expressing lithology. Right? Can be used to interpret lithology. Things like gamma ray and SP for classic environments. So you can find those kinds of patterns if you know how to do it. Okay. You can also use other kinds of things like core can also be used. core is nicer, but it's going to be most of the time it's not going to be a very thick succession, right? Okay. So just what we've looked at the large scale. We look at now these smaller windows. Nampak bahagian kecil je stratigraphy dia. Macam mana kita nak interpret dari segi sequence stratigraphy. Alright, so any questions up to now? Tak ada, eh? Alright. Okay. Now, I mentioned earlier, you will have different kinds of patterns to the stratigraphy depending on where you are in the basin, and there is a reason because of that. That is because of Walter's law. Different places, different fascies, right? Right. So you have different environments happening at different water depths. Different parts of the same system tract, macam HST ni, will represent different depths in environments at different water depths. So if you trace at the HST system tract here, so the fluvial here, maybe it's going to be coastal deltaic here, more shelfal marine here, and deep marine here, right? Also the same thing with the low stand here. The lower part is going to be lots of turbidites here, kat sini. It's going to be more deltaic here, and more shallow marine, and even fluvial at the top. Because it's prograding, it's shallowing, right? So vertical fascies arrangement and stratigraphy will differ, akan berbeza dalam masa bila kita guna differ depending on location in the basin. Mana you berada, dia punya stratigraphy berbeza. Tapi kita boleh interpret lah. So it's not just, oh, I don't have seismic lah, data saya tak cukup, ini je saya ada 2-3 log saja, bos. Saya tak boleh buat apa lah, saya balik rumah lah. No, we cannot do it like that. We do our best. There is never enough data. Saya akan ulangi sekali. There is never enough data. We just do the best that we can. Kan? And that is our job. Our job is mostly interpreting based on our knowledge. Okay, so you get different kinds of vertical sedimentary successions at different positions within a sequence. So yeah, you can use gamma ray log would be nice. Gamma ray log and fascie successions, different positions of the basin. You get, but the general pattern is this. If it is LST, most of the time it is sand prone. Means that it's going to be, most of the time it's going to be sandy. Okay. So anybody has an idea why is it going to be sand prone? Kenapa banyak sand masa LST? Any ideas? No? Okay, so yeah, if you have an LST, meaning that, what that?
Higher energy.
Kenapa you have higher energy masa ni? Why do you have high energy during the LST?
Not sure rather.
Okay, but yeah, that's a good step lah. There is higher energy during this time. That's correct. Yeah, and the reason you have high energy, lots of different things. First, there is a relative sea level fall, kan? When there is a relative sea level fall, sometimes the relative sea level fall is very low. Now you get the all the shelf is exposed and also the slope, and because of this, you punya it's going to be unstable. Okay, you punya rivers to not in balance anymore, so dia akan menghakis ke bawah, it's going to erode. And when you have higher rates of erosion, yeah, there's going to be lots of sand being transported lah further down towards the basin. Okay. Okay, so yeah, during the LST, it's going to be sand prone. During the TST, it's going to find upwards. Because most of the time, if it is shallower, yeah, the general trend lah, it's like this. If you have shallower in a coastal environment, it's going to be higher energy, so you have sandier deposits. If it gets deeper, you're going to get further and further away from the sediment supply, which is the land, so it gets finer and finer grain. So because it is transgressing, sea level makin lama makin naik, is rising, so it gets more and more, it gets deeper and deeper. So it becomes finer and finer grain. So sand, muddier and muddier. That is a usual pattern you get in the TST. And for the HST, because it is shallowing upwards and the aggregate and prograde, the prograding, so it's most of the time it's going to be costing upward. So that is a nice pattern you usually see when looking at sequences, right? So for example, here I have sedimentary logs for different parts of the basin. So towards my right is deeper, it's towards the basin. Towards my left is land, towards the land. Okay, so I have alluvial plain here and abyssal plain on this side. You can see environments like slope, shelf, and so on. And you have you have a sequence boundary at the top and another one at the bottom. So between this is a single sequence. Okay. Now look at the patterns, kan? If you are in the deep marine environment, this is what you get. Sand prone bawah, then it's muddier during the TST. It will be the muddiest at the MFS. Okay, sini the MFS. That's the MFS, the dashed line. And then, because it's shallowing again during the HST, you get a costing upward. But the environment in this case, going from turbidites at the bottom, turbidites, the sand is turbidites, going to marine, and you have shelf at the top here. Right. Okay. So yeah, when you go to other parts, the pattern is still the same but different fascies, kan? Sini on the shelf itself, you have fluvial sandstones at the bottom, followed by shelf deposits, and it's finding upward during the TST, and then it costings upward again during the HST. But the same pattern gitu. Sand prone ke bawah, finding upward, and then costing upward, and the cycle continues. Further landward, it's more subtle. You can get that kind of pattern, but it's a little bit hard to identify lah. Can't find a marine maximum flooding surface in here, for example. But you do get things like this lah. It's sandier during the low stand, and it's going to be muddier in the middle. Right? So that's the general pattern you get in sequences. So let's look at different parts of the sequence. Yeah, let's look at the different areas in your basin and see how the different systems tracks are expressed. Yeah. But for today, I want to look at the shelf only. Saya nak tengok bahagian shallow marine ni saja. I don't want to look at the fluvial environment that much and also the deep marine environment. We'll talk about those areas in another lecture. Okay, so just look at the shelf part. Okay, so in the middle, see what kinds of patterns we can. Okay, so we go one by one through the different systems tracks. We have the low stand systems tracks, LST. So it is very slow relative sea level rise just after a relative sea level fall. Okay, this is what you get. I've seen this cartoon before, dah nampak dulu. Saya dah tunjuk dah. So you have an unconformity. You can trace it in these three areas, the three wells here. Unconformity. So below here is the older previous high stand systems track in HST dulu. Notice in some parts, you have a nicely preserved high stand systems track, HST. Nice costing upward, progradational parasequence sets. Ini kan, satu parasequence, 2, 3, 4. And on the other side, you can also trace it to this one here. It's the same pattern, right? But in the middle, the erosion is deeper because you have a river flowing through here. Ada sungai kat tengah. So you have a river valley, and this is called an incised valley. So what happens inside the incised valley during the LST? The incised valley was formed during the FSST, when sea level was falling. But now it starts to become filled in with sediment because sea level is rising, but very slowly, kan? So you start to get fluvial deposits being deposited inside your incised valley. So because you have rivers, sea level is rising slowly, so fluvial deposits can fill in the valley. So whether fluvial channels, can have floodplains, channel levees, crevasse plains, and so on. Okay? And these are going to be very sandy deposits. Kan? So that is what is happening inside the incised valleys. Thick, aggradational, sand-prone fluvial deposits. Right? That's characteristic of the LST in incised valleys. But that is what is happening inside the valleys. Kan? Dalam lembah sungai macam itulah. But what is happening away from the incised valleys? This is going to be higher ground. There is still an unconformity because there is subaerial exposure. Bagi tanda tinggi sini. So, but rivers are not flowing through here. You only get soil forming. Pembentukan tanah, there will be soil being forming here. It can be very thick sometimes. You have roots, desiccation cracks, soil, leaching, and so on. Yeah? But no really thick deposits of the LST being formed. So here, you don't have an LST being preserved. Missing. Okay. So thick LST in the incised valley, missing LST on the interfluves here. Okay. So here, what you see is HST, LST goes to TST, right? That's supposed to be the pattern. So it's finding upwards at TST. But away from it, on the interfluves, you go from HST, unconformity, TST, no LST being deposited. On the interfluves, there is no significant deposition, only soil formation. Right? So just HST, sequence boundary, TST. So be careful when you're trying to interpret sequence stratigraphy. Sometimes system tracks can be missing, boleh hilang, depending on where you are in the basin. And I'm always repeating, depending on where you are. That part is clear, yeah? Any questions? Okay, so if no questions, I'm going to move. If you have any questions, just interrupt me. Yeah? Mencelah aja nanti. So just to show you some pictures to help you visualize kan, how does the stratigraphy of incised valley fill look like and how the interfluves look like. So this is a nicer cartoon from a paper. I can share with you the paper on Spectrum later on. And what you get here is a cartoon where you get this incised valley here being drawn. This is the incised valley. And it's cut into older HST parasitic set here along the side. So notice here, you can see that it is made up of the HST, the older HST is made up of stacks of parasequences, so parasequence set. That's one parasequence. You can maybe it's going from pro delta to delta front. Okay? And the top is even see some rootlets there, probably delta plane. And then you have another flooding surface and another flooding surface, another flooding surface. So you have several parasequences. In this case, it looks like it's air grading, it's mostly air grading. And you see the same kind of pattern on the other side. But in the middle, all this has been destroyed, has been cut into. Dipotong. And you have an LST fill at the top here. Remember, this incised valley fill is younger compared to the side here. Tak sama umur ni, walaupun dia sama level. Although it is the same level, it is not the same age, this is much younger. It can even be significantly younger. Maybe it's 100,000 years or 1 million years. So be careful when trying to correlate. And inside the incised valley itself, what you get, cross-bedded sandstones, conglomerates, inclined strata, maybe made up because of point bars, because of lateral migration. And you have mud-filled channels, because these are your oxbow lakes, abandoned channel fills. And you also have floodplain shales and coals, right? Local preservation, non-channelized mudstone, coals, and paleosoil. So fluvial deposits inside a valley. So these are incised valley deposits, right? And away from the incised valley, this is your unconformity, right? Your line here goes down, it goes up again, and you have soil formation. And this is your interfluve area. This is also your interfluve area. Okay. So another cartoon here, the LST incised valley fill in the middle here, the darker gray here. You have cross, it's just to show you channels here, again. And away from it, you have interfluves. And yeah, so you get one thing, interesting thing about incised valleys, if it is preserved in the rock record underground, this is how it looks like. It's going to be a lens of sand-prone deposits is going to be encapsulated in thick mud. Keliling dia lumpur, banyak batu lumpur, mudstone kan? When you have a thick lens of sandstone in the middle. Now, this is important because this can be very nice hydrocarbon traps. Okay? Maybe there's oil inside your incised valleys, and it's inside your reservoir is sandstone. It cannot go out anywhere because you have a thick mudstone at the top. It's going to be impermeable. There's a seal there. And laterally, it is also sealing because you have thick mud along its side here. So it is trapped in the middle here. You have a nice, what we call a stratigraphic trap. Okay? So not just for hydrocarbons, also for other kinds of resources. You can use this kind of visualizing things. Seen this photo before. So this outcrop at Labuan shows you a sand-prone succession here with a basal unconformity. And it's overlying marine shales at the bottom here. And this has been interpreted as an incised valley fill. You can actually trace this sand body here with conglomerates also for long distances along Labuan, along the western coast of Labuan. Okay, so for at least 10 kilometers. It's actually the fill of a very large incised valley. So you have a subaerial unconformity separating the HST marine deposits at the bottom and overlying LST fluvial deposits at the top. Okay. And how does the fascies look inside your LST here? You have thick, coarse, multi-story, amalgamated, channel filled sandstones and conglomerate. So I labeled here. This is HST semua ni. Ignore this part. This is a boulder coming from the younger part here. It's going to be muddy sampai ke sini. Any questions?
No for me, Dato'.
All right. Okay. So if no questions, let's move on. Just use some more examples of LST deposits on the shelf. So this is not outcrop. This is from a sample of core. So you have a borehole. You've made a well. You've already run tools inside the gamma rays. You can also extract rock samples in cylindrical shape. Bentuk cylinder. You take it up. You slice it in the middle. And when you cut it like that, you slab it, you see, you can see nice lithology, stratigraphic contacts, and even sedimentary structure. Here we see lamination, nampak those streaks, lighter color. Those are ripples here, graded laminations, scours. In the sandstones themselves, the lighter colored here, coarser grain intervals, cross beds. Notice the faucets are dipping towards the right here, and lamination and so on. Okay. And if I make a sedimentary log of this succession, going from older, this side here, to makin muda ke sini, ke kiri, younging towards the left. Okay. So this is a sedimentary log. The core represents this part here. So here, this is muddy, representing this part, and this is sandy. You can even see I've drawn here cross beds here. Yeah. This is going to be this part, and that is the contact. It's sharp. Mud, boom, coarse sand. Right? So it's a sharp contact. It's not nice, coarsening upwards, slowly going from mud to sandier to sandier. It's because mud, boom, gitu. You can even see it on gamma ray log. So this is a gamma ray log for this part here. And notice here, I need to balik lah saya buat. So better I need to repair this. So it's this on the right hand side is high gamma. This upside, this is the other way around. On the left hand side is it's supposed to be low gamma. Okay, so this is error. This is my mistake. So you should have mud shalier parts should be high gamma and the sandier parts should be low gamma. Okay, so you can also see it here on the gamma ray. High gamma shale, and suddenly it goes to low gamma here, and followed by a blocky sand. So this is your LST deposits. It's mostly fluvial channel deposits, form of sandstones, conglomerates, and they're amalgamated. That's one channel deposit. Another one here, and that's your erosional surfaces. There's another one, and so on. And you also have floodplain deposits associated with it. Some of these channels are finding upwards. So you have things like mudstone with roots and ripples at the top here, right? So it will be a point bar deposit. And the bottom part here is going to be the HST. These are deltaic deposits. Right? And you have the sequence boundary here between the deltaic deposits and the LST and the fluvial LST deposits. So I've also already marked the sequence boundary here, the unconformity here. Okay. So a nice example of a sequence boundary. This is from offshore Sarawak. Yeah? This is Miocene age. The outcrop before, I should mention you these kinds of things also. So you have this picture here is from Labuan, and this is also Miocene age. Okay, so that's the low stand. Let's look at the TST, the transgressive subsidence tract. How is it expressed on the shelf? Macam mana rupa dia? Yeah. So the vertical succession is going to be transgressive. If it is inside the incise valley, what happens is there's going to be an environment change. Originally, the environment was like this, right? You have rivers inside your valley. It's fluvial. And the sea is further towards the right here, because it's lower sea level. But then because of transgression, what happens is that sea level rises, the river itself in the valley, near to the mouth, is going to be drowned, ditenggelam. That is one worrying thing about relative sea level rise, is that all these river valleys, which are river valleys, will be drowned during relative sea level rise. So you get lots of cities which are built associated with river mouths, right? And all these cities will be drowned. So that's something when we talk about climate change. That is what is worrying about relative sea level rise. So we know this from ancient rock record. So what happens? Relative sea level rise, what was once river is now estuary, jadi muara. This is no longer fresh water. This is marine water, seawater along the mouth here, and also brackish water, air payau. Right? So you have an estuary. No more rivers. Rivers are pushed further landward, further backward here. Okay? So basically, your fasces is also being pushed further and further landward. Okay? And because of this, you get a retrogradational pattern. Right? What was once fluvial is now marine. So a cross section here, a sedimentary log here, inside the incise valley. So before we had low stand, you had the fluvial deposits. But above it, we have the TST. And sea level is rising. What you get is a fining upward pattern. Because it's getting deeper and deeper and deeper. And the fasces, if you look at it, nanti, it's going to be more and more marine. No longer just fluvial deposits, maybe some tidal deposits or even shoreface deposits at the top. Right? So that's an expression of the transgressive system stack. The same thing also occurring in the interfluves. So you get deeper water fasces compared to the lower part here. So you get a fining upward pattern also here. Just one thing to remember, inside the incise valley itself, kan, it's not all just LST tau. Dalam ni, you can also have at the top a little bit of the TST being preserved inside the incise valley itself. Right? Okay. So transgressive succession, your incise valley will be drowned, akan tenggelam. Estuarine deposits can fill in the upper part of the incise valley here. Along the interfluve, you get a transgressive marine succession. Things like delta, shoreface, and shelf deposits. So this part clear, yeah?
Okay, Doctor.
Okay. So I'll show you examples of sedimentary successions on the shelf representing TST. Excuse me. Okay, so this is a sedimentary log showing you half of a sequence, part of the sequence. You have the sequence boundary at the bottom here, followed by LST, fluvial deposits. And then you have a TS, this is the transgressive surface, no? Marks the initial transgression. Then you have the TST at the top. And your TST is going to be fining upwards. So in this case, you have estuarine to coastal plain deposits, maybe tidal channels, distributary channels, and so on. And because more and more marine as you go going further above. Notice there are lots more bioturbation. These symbols here represent burrows. Yeah? So more bioturbation at the top because it's getting more and more marine. And it's going to be the most marine, the deepest fascies will be here. Once you reach the deepest fascies, this is going to be the maximum flooding surface. All right. So the base of your TST is going to be marked by the transgressive surface. This is it in dashed line here, TS. The boundary between fluvials ini and marine and estuarine deposits at the top. That is the marker for the base of your TST. Then you have a gradual upward deepening of the fascia. It gets more and more marine as you go moving further upwards. And the top of your TSTs ni, it's going to be marked by a maximum flooding surface, the MFS. It's going to be here at the MFS, you're going to have the deepest fascies in the vertical succession. After that, of course, the HST, yeah. So it goes back to shadowing upwards at the top. Okay, so the TST fascies can vary depending on what kind of environment you have. Ya. Sekitaran berbeza lain beberapa fascies. Maybe if it is tide dominated, you have tidal channels dan TST. But if it is wave dominated, you have shore face. If it is fluvial dominated, you have delta. So depending on the energy, the environment, you get different kinds of patterns. But overall, macam gini, pattern ni senang je. It's going to get more and more marine. Okay. So in this case, you have fluvial at the bottom here. This is your LST, TS. Transgression, finding upwards. What you have here is parasequence sets, delta. And then you reach the MFS, then it goes the other way again, regression. Okay, so just remember, again, away from the fluvial valleys, it's going to be hard to identify the sequence boundary. So tadi, when we're working with incised valleys, it's easy to identify the SB. Just trace it, and then you have a thick sand, or that is the incised valley. So the base must be a sequence boundary, very easy. But what about the interflows? When you are away from the valley, jadi susah sikit. Away from the valley, it's going to be hard to identify the unconformity. Oops. Oh, okay. Going back to this. It's okay. We're recording this. Let's see if the student tries to get back into the meet. Okay, so away from the incised valleys, what you get is like this. Bawah dia HST, the bottom part is HST. So what you get is deltas, right? So prograding. But because there is no LST, the top part is TST, the same thing. Above it, it's going to be TST. It's just going to be a thin shale layers in it. That's the most marine part before you go to the MFS. Followed by another HST. So bawah sini HST, atas HST, and just there's going to be a shale here. It's going to be very hard to interpret this as a sequence boundary. If it is just you only get these two logs, and you don't have an incised valley, you might miss this. You mungkin terlepas pandang. Delta, marine delta. So that's a marine, that's just a flooding surface, so nothing happening here. But there's supposed to be a sequence boundary here. Okay. So away from fluvial valleys, it is harder to identify the sequence boundary and also to identify the TST. It's just shale. But one tip to have is this. If you have a thick succession, the shaliest part of the succession, most of the time is the MFS. So this will be thick shale here. So most of the time, this is going to be part of the MFS here. So if you have an MFS here, so the low part here is going to be the TST. But there is going to be some uncertainty. Just limited data. So in this case, I'll just call it a sequence. A candidate. Ni calon je lah. So this is a candidate sequence boundary. I'm not that sure in this case. It'd be nice if I have another well here showing an incised valley, but it's consistent with sequence stratigraphic principles. There could be a sequence boundary here. So it is a candidate. Not 100% certain, but maybe. Right. Okay, so the last system struct we'll look at is the HST, and let's look at the expression of the HST in the vertical succession. Yeah, so it is going to be above the TST here. It's going to be the shaliest part here, but it's going to shallow upwards here. So what you get is an aggradational to progradational succession. It's going to be capped by an unconformity. Okay. So aggrade, prograde, posting upward. Then you have a sequence boundary at the top. In some places, it's going to be missing because there's going to be significant erosion. The HST is going to be represented by a succession of coastal marine parasequences, maybe delta, shore face, or shelf. Parts of the HST may be missing if eroded by an overlying subaerial unconformity. Okay. Another photo showing you an outcrop. Yeah? Look at it in cross-section, rata rentas. You've seen this photo already before. So remember this is cross-section, and you have a relatively perfect sequence here. Yeah? So red marks your sequence boundaries. And so let's see what we have. So the bottom part here, you have marine deposits. So gray is shale, and then you have a thick sandstone here, but it's still a marine sandstone. So you can interpret it as being a progradational pattern here, right? It might be a parasequence here, right? So this is interpreted as the HST. Then what happens is that at the top of these marine deposits here, you have an erosional surface marked by red here, right? And it goes up and down. Here you have shale below the sequence boundary, but towards the right, the shale is eroded into, it disappears, right? And that tells you that it is erosion, and you have truncation here, has been cut into, right? And above it, you have fluvial deposits. So these are channel deposits here with overbank deposits, right? Here, the fluvial deposits are separated from the marine sandstones by a thick shale, but towards the right-hand side, it is almost in contact with the marine sandstone below here. It's amalgamated now. But environment-wise, it's different. Marine, deeper, fluvial. Right. So this is an abrupt change in facies. This is a sequence boundary. And in this case, it is a subaerial unconformity, going from deep marine to shallower fluvial. And aggradation due to slow rise in sea level. So this is the low stand. This is going to be the incised valley fill. You don't see the margin of the incised valley. Maybe it's going to be further away from here. Yeah. So, but it's still, yeah, it's lots of amalgamated channel fill deposits. This thickness is going to be something like 30 meters from here to here. You can see trees here along the side here, right? Now, from the fluid deposits, above it, you have thick shale, which is marine, right? So you go sand, and suddenly it goes into marine shale. So this is a sharp surface. This is going to be your transgressive surface, your TS. Kat sini lah, lebih kurang kat sini kan. That's your TS. And above it is your TST. This is the shaliest part. Somewhere in the middle here is going to be MFS, and below it is going to be the TST. So here, somewhere here is going to be your MFS. And above it, you get another coarsening upward package. Maybe several parasequences. One parasequence here going from shale to sand, shale to sand, shale to sand, and several parasequences. So it's a aggradational to progradational parasequence. This is the HST now. And then above it, another fluvial deposit. It's also thick, about 30 meters thick here. And this is your LST. And notice here, the erosion surface is irregular. Here is cutting into the HST. Further towards the side, it goes upwards gitu, and your sand becomes thinner. Right? And here, you just have marine deposits, and above it is still marine deposit. It's hard to identify the sequence boundary here. Okay? So this is another LST. There's going to be a thin TST in the middle, and then another HST at the top, and the cycle continues. So that is a single sequence. That is how it's going to look in outcrop. So here is quite a clear pattern because the outcrop is very wide. Right. This is going to be several hundreds of meters wide, so clearer to see. But if you only have a log like this, you're going to need to rely just on the stratigraphic pattern because you don't see the geometry. Okay, So the main point of today's lecture is this: different parts of the shelf, bahagian-bahagian lain the basin you, you'll get different patterns, vertical patterns to the stratigraphy. But there is an overall overarching theme: sand-prone LST, finding upward TST, coasting upward HST. Those are the general patterns. If you look at the small details, there's going to be lots of variation. Ada perbezaan, tapi kecil-kecil. But the overall general trend you must know in order to interpret sequences. Right? So here, fluvial, even though it's fluvial, you can see it's going from sand-prone bottom, finding upwards. The shaliest part is the MFS. And then you have the HST, which is coasting upward. Some parts of the estuary fluvial, maybe it's going to be a little bit more difficult to identify. But if you know the fascies, you have core, it's easier. And you just see the change in the environment. Fluvial at the bottom, LST here, followed by TST, which is more marine. Somewhere here is going to be the maximum flooding surface. But it's hard to find because everything is, the gamma ray signature is roughly the same, yeah, not much difference. Yeah. So it's going to be more difficult. Deeper areas, maybe look something like this, going more sandier sample at the bottoms, finding upwards, and MFS here, when it shallows upward again, and that's the HST. Right? So yeah, you get different vertical patterns to the stratigraphy, different places, because you have different environments, and that is consistent with Walter's law. Okay, any questions?
No for me, Doctor.
Alright, just on time lagi tu. So see you on Wednesday lah untuk practical. Right?
Okay, Doctor.
Thank you, Doctor.
Alright, welcome.